Okay, so this is lecture 2 of this course this summer. I have very humbly titled The Basic fMRI Study, All Elements to Consider. With hindsight, that might have been a little bit too expensive, but we'll see how we go. Now can I, yes. So, what is the basic fMRI study? You start with an MRI machine. You throw some people into the MRI machine. You publish papers, you become famous, you get money, you change the world. Okay, so I think we're done for today. Any questions? No? Okay. Okay, bye. So I'm being a little bit joking right now, but I think especially in the early field, when the field was sort of building up, there was a lot of papers that sort of, took this approach of just, hey, we've always done X. Now we can suddenly non-invasively image people. We can, I studied driving, I study emotion. I'll throw someone in the scanner and collect data, and now I have the neural correlates of driving, the neural correlates of emotion. So I kind of, there's a very long history of these neural correlates papers, and I'll say I just copied a bunch of these from 2001, which was kind of on the early side of these studies building up. And I don't want to single out some of these are quite good studies. Some of these were good for their time. Some of these are terrible, but I think it puts this idea of like, this is what you can do for a study. Just put someone in a scanner, you get neural correlates, and you're done. And this isn't quite over yet. So it's still a very common thing. So every time I see an article that says neural correlates, I get a little smile. But we also have other examples of this kind of going forward. So like many of you who have done MRI studies, there is a huge push on sharing data. And very often I hear like, oh, I just downloaded this data set from the internet and I used it. And in some ways it's the same general idea that like the technology exists, it works, everything is perfect, and we can just download a data set and use it. And sometimes there's a lot more interesting stuff that goes on underneath. So if any take-home message from this talk is to think a little bit more beyond why and how we do something. So what are my goals of this talk? I think my main goal is to help people learn the key phrases of fMRI study design analysis and to understand the types of decisions that researchers need to make in each phase of a study. What I'm not going to do in this talk is have you all learn the best options for every phase of the study, or explain all fMRI study designs and analysis methods. That is, as you'll see as I go through, there's way too much there for 1 hour or maybe even the whole summer course. But the idea is to give you a sense of what's there, what questions to ask, and what to think about. And I'll also add as I'm going through, questions are great. Please, if you have questions as I go, I'm focusing on a few examples here and there, but both online and in person, I'd much rather find out that I ran out of time because I was interrupted with a lot of great questions than get to the end and have everyone quiet. So please interrupt. Those are the best examples in any study, in any talk. So I also just want to, since I know some of you have been in fMRI for a while, some of you might be, just starting out and learning things. I want to sort of explain a bit more why I can't cover all the details of fMRI studies. There's a massive amount of variation. I mean, fMRI is a really powerful tool, and there's a lot of stuff we can do with it and many different study designs. So if, for example, a lot of the early fMRI studies, I would say, are task fMRI, with where you put someone in a scanner and you have them do something. And while they're doing it, you have a model of like, shining a light. These are the times you're shining a light. You fit it to on every single voxeler point in the brain, you fit to the data. And those are the core results of a paper. So this is like one example paper of that type of study. There's resting state fMRI studies, which are correlations between different voxels across the brain, let's say in predefined conditions. You can again do a similar task fMRI, but then you can push spatial resolution, which adds all these other questions and design decisions on how do you get these, much higher resolution. You can have task fMRI that isn't just, this voxel isotope to a model that uses like pattern analysis across clusters or groups of voxels in regions. You can have studies that, with either task or resting fMRI, that use whole brain connectivity measures and other analysis methods. And you can use things like what's sometimes called naturalistic stimuli or movies where you don't really have a task lock design, but you're looking how signals across different brains fluctuate in sync with each other. And these are just 6 examples, all from the same lab. So a lot of people do a lot of different things, and I've tried in this talk to give examples of stuff that apply to all of them, as much as possible, as opposed to focusing on any specifically. So now a slightly more serious basic fMRI study. And this is also going to be kind of the talk outline. So you'll see how, how I'm going to try and frame this. I would say the first thing in any fMRI study, and really any scientific study, is getting a clear scientific question. What are you trying to answer? And designing what the study is. So if you're doing like a task, it's designing the paradigm and figuring out what it was, and also designing what MRI parameters or acquisition things make sense for your study. If you're not coming in with a good question, whether it's then that's going to be a big challenge going forward. The next step is what I would call piloting. So you have your question, you know what you want, you know your goals. Then you're going to sort of collect, a small data set, trying to figure out like if your plans for a study are good. It could also include behavioral measurements and other stuff as well. The next phase I'm going to call data collection protocol. So you've piloted, now you want to make a design of how you're going to organize your study. So what does it mean when you bring someone in, and what are they going to do? Exactly what you're going to be collecting, and how you're going to log and keep track of it. Next is data collection. And next is analysis interpretation, which often is a lot more in front of computers nowadays, but it's also discussion and speaking with other people. And finally is communication. So you have your results, you're potentially sharing code and data. The last big thing I want to share with this overview is quality assurance or quality assessment. So QA or QC. And I think this is sort of the critical step that locks everything together. So at many of these phases, you want to sort of set up rules and metrics for saying, what I expected to collect is actually what I'm collecting, or what I need to collect is actually what I'm collecting. And that is a continuous process, as I'll be discussing further on in the talk. And I'll say, since a lot of people are not acquiring data, fMRI studies also use existing data. So I'd say this is the model I just showed you. For existing data, it's fairly similar. You're still starting with a scientific question in study design. Your data processing protocol can be focused much more on your analysis methods and organization. And then with that, you identify shared data instead of collected data, but everything else stays the same. But again, the one thing I want to stress is quality assurance is central. I'll get into this a bit later, but just because someone has published a data set does not mean it's good. And more importantly, just because someone published a good data set does not mean it's good for your scientific questions. And if you're not checking the data with quality assurance with your questions in mind, you can end up in unhappy places. So that's the general outline. I'm going to pause a bit. Does anyone have questions so far, or should I jump into them?
None in the chat.
Okay, none in the chat. Okay. So scientific questions and study design. What are we going to collect? The core question is really, what types of data have the potential to accurately and effectively answer your scientific question? And in some ways, this seems like an obvious question, but but especially with MRI where we have a lot of options of what to collect and we're always balancing different things as I'm gonna be discussing a bit. Deciding what you need is actually a very critical step. From your paradigm, do you do a task? Do you show them movies? Do you do rest and just tell them to sit in the scanner, eyes open, eyes closed? And if you're doing that, which task, which movies, what do you mean by rest? Similarly, we, in a lot of discussions of fMRI, we focus on the fMRI part, but there's options with structural and other scans as well. So do you just need a structural MRI to align to, anatomy or align to sort of a common space? Or is it useful to have structural fMRI that has clinical information like lesions or strokes? Is it useful to have structural images that might help correct for warping or other distortions in the data set? Depending on the study, is tractography or other information on anatomical connections useful? And even for the fMRI, calibration measures I feel like aren't used that often. But there are sometimes things you consider, especially in clinical populations, where you might have, let's say, different vascular differences between populations. And you might want to sort of make sure that your results aren't just modeling the fact that an elderly population has more arteriosclerosis and slightly lower dynamics in both signal. Also worth considering what simultaneous acquisitions are worthwhile. So I'll talk a bit about pulse and respiration on the next slide, but we have, at least here, we have setups to do EEG simultaneously with fMRI. It's a bit of extra work to set up. And there are some studies where that's going to be a game changer for the study, and some studies where it might be beneficial, but not as critical. Similarly, eye tracking is both useful for cognitive tasks and understanding how people are focusing on the task, but also extremely useful on saying, is a person awake? Which I don't know how many people have been in MRI scanners, but it's surprisingly easy to fall asleep in something that's really loud and claustrophobic. And then there's, topics like participant responses. So like if you're doing a cognitive task, it might make sense to record button presses and store them, but designing what you need to record and what's useful is also critical. And lastly on this slide is who to scan. Depending on your study, do you want, I'll get to come to this again a little later, but lots of data in a few people? Do you need a really large population to sort of see, population level effects? Or you need enough data to compare across different populations? Do you really want to focus in differences in person? These are all decisions that are going to affect how you design your study. Any questions on this so far? So I'm not going to sort of go into details on all of the sections, but I want to share at least one cautionary tale of an example of why I think thinking about these peripheral measurements is so critical. A lot of people talk about respiration and cardiac as noise in our data because they also affect the gold signal. I'm giving a lecture on noise in a few weeks, so I'll cover this a little bit more then. But they're also, even if you're not like actively regressing them out through noise removal methods, it's useful to know, to record them and know what they are. So this was actually my second first author study ever as a grad student. And you can look at it, I'm very proud of this paper, 2007. And we showed flickering checkerboards to people, 200 milliseconds each. We calculated hemodynamic responses. I showed differences in these different brain areas between younger and older populations, lots of other stuff. It's a nice study. I think it's mostly held up. So that was the part that I published. Here's the part I didn't publish. This was part of a larger study on trying to understand nonlinear responses in the gold signal. So how does the fMRI response change if you're showing a 200 millisecond stimulus versus a 3 versus a 6 versus a 12-second stimulus? Because we know there's sort of a bit of a nonlinearity there. I wanted to see how it varied across aging populations. The trouble was a non-trivial number of my volunteers held their breath every time the checkerboard appeared. So you show a 3-second checkerboard, they hold their breath for 3 seconds. You show a 6-second checkerboard, they held their breath for 6 seconds. And breath hold is actually one of the most robust ways tasks you can do to get bold responses. So if you hold your breath, your entire brain is seeing a rapid blood flow change everywhere. So you look at these results, they're gonna be beautiful. I'm gonna see beautiful responses to a 3-second checkerboard and beautiful, huge, bold responses to a 6-second checkerboard. But it has nothing to do with the checkerboard. It has to do with the fact that they were holding their breath. So these data were effectively useless because I intended them for one purpose and I could not use them for that purpose. It's not even like a null result. It is just bad data. So the big take home message from this is if I didn't collect this respiration data, I would have not noticed this. I would have not noticed they were holding their breaths. I would have had visually appealing results. And those appealing results would have been published and they would have been wrong. So I think this is just one example of sort of like when we're thinking about a study and how to design a study, thinking about these details like, do I want respiration cardiac could be an aside, but also is a central part of, this design process. So continuing on this, there's also study level questions. When we're talking about number of participants and amount of data, are we looking for individual level effects? So if you're looking for an individual level effect, that means that you're going to want the data in every person to be as high quality as possible. So that if you're doing a contrast or connectivity or some other modeling, you're going to want good temporal signal noise, good signal noise, and that could be done by either collecting data that every volume has a strong signal, or collecting a lot of data. So even if with the layer, there are a lot of studies you do with really high resolution layer studies, where any individual image is pretty low signal quality. But if you're collecting 20 or 30 minutes of data per test condition, you can get a much better signal noise for those tasks. So if the focus of a study is these individual level effects, then making sure that you have results that are visible on the individual level is critical. If you're looking for consistent group effects, then I still think individual, you want some level of data quality on the individual level, but it's less important. But maybe you're going to want more subjects. So you're gonna need a lot more subjects to say this truly represents a group. And there's a lot of arguments in the literature of how big a large population is. And I think part of the reason is that argument is, like I said, that there's the individual data quality and then there's the group data quality. And I think a lot of people are sort of saying, if I have really bad data on individual subjects, I need a giant N. And I think a lot of this discussion is not focusing that if your individual subjects are slightly better, maybe your full sample size doesn't have to be quite as large. But this is another question to think about as you're designing a study. And then similarly looking for behavioral fMRI response variation across participants. If you want to say that there's an individual trait or response difference, then you're back onto this individual level effect. So even if you might need both, you might need a big population because you're looking for a trend, but you also need robust enough individual data. So it's to say that, a measure in one subject is consistent enough that we can actually measure these trends. Similarly, if you're looking for diagnostic treatment or relevant markers, the end result is you need something that is measurable in an individual subject, but you also do need that bigger population. My last point on this slide is a lot of people talk about statistical power analyses, which is as you're designing your study, you say things like, I am expecting to see a 1% signal change, or I'm expecting to see a behavioral effect that is varying by 0.2% across populations with a whole range of 2%. So you can put these numbers into a power analysis, and it's sort of a rubric for trying to figure out how many data sets you're going to need to do that. I think as you're designing a study, this is very important. But I also think, especially in the field of neuroimaging, it can be overemphasized and oversimplified. So there's other things, because I think power analyses very often focus on sample size. And in our field, we have, like I just was saying, we have sample size, but we also have a lot of ways to adjust data quality. So if instead of saying we have a 1% signal change with, 0.5% noise, if you're measuring in an individual subject, if you have a 1% signal change with 0.25% noise, then your power analysis radically changes. So I think, thinking about power analyses is important, but it's important to think about these in a holistic way, where you're thinking of the different ways you can build power and get towards a robust result. So, also with this, the other area I'm going to focus on in study design is acquisition parameters. And if my message isn't coming clear yet, there are no universally best parameters. And the parallel to that is never copy the parameters from another study without understanding why they made those choices. So if anyone here goes down to the scanner here, or anywhere that's fMRI, you'll find other people's studies and they'll have their fMRI parameters, and it's very easy to say, hey, Josh knows all about fMRI and he designed this study and his parameters are great. Like he had to have chosen good parameters for his study, so I'm going to copy his parameters and use that for my study. This is a really, I've seen this cause so much trouble so many times, because like I just said, different studies are going to have different goals. So even if you have the same parameters, it might be good for one study and bad for another. So the questions that derive this, that interact with acquisition parameters. So there is brain coverage. So there might be a study that says, I want to always get the entire brain, including the cerebellum. There might be another study that says, I'm actually studying the motor cortex. I need to make sure that I reliably get the motor cortex and nothing else. There's also a common issue of dropout with fMRI. So I'm not sure if Peter talked about this at all on Monday, but you'll definitely hear about it in other lectures across the summer, which is due to some acquisition, due to the way MRI data is acquired, there are certain areas like the orbital frontal cortex, sometimes temporal lobes, and other places where we just lose signal. And there's different ways you can tweak your parameters to make that signal loss better or worse. And there might be one study where they don't really care about the orbital frontal cortex. They don't have any specific questions there. And the fact that the data is distorted there doesn't really matter. And there might be another study where not getting the orbital frontal cortex means that you're not getting good data. There was I've definitely heard scenarios where someone collected a decent sized data set and discovered after the fact that a key region of interest wasn't reliably in their sample. So this genuinely happens. So thinking about what areas matter and looking at your signal is critical. Similar to dropout is distortion, that there is some different acquisition parameters will make your images more spatially distorted or twisted in space. And being aware of that and thinking about what levels of distortion matter or not is also key. A common term that comes up often is temporal signal to noise ratio, which for most of fMRI is the mean divided by the standard deviation of, sometimes detrended of data, which when you're not doing something, ideally it's in a phantom, which is the jar of oil. The basic idea is that if you're with your acquisition parameters, if you have a jar of oil in there, the signal doesn't change. So the more that it's fluctuating over that, the worse your signal to noise is, temporal signal to noise is, and the worse the signal. You can also measure this in brains, and there's actually, I shouldn't say ideally in like jars of oil, because there's different factors that affect temporal signal noise in brains, and getting a measure of what it is in brains is critical. The only difference is we actually do expect some fluctuations in the brain. So like in theory, with the jar, a jar of oil, we can get it up, a perfect signal to noise of like, thousands, but not an MRI, but like in theory. But with a brain, you're always gonna expect some noise because there's gonna be things that make our signal vary. And then head motion sensitivity, there's gonna be some sequences and some choices where if someone moves their head a bit, it's just part of the data, we can mostly correct that later. And then there's some studies where, it's absolutely critical and that you either wanna work hard to make sure people don't move their heads using physical planning in your study design, like, different ways to help people keep their head still, or pull sequences that are a little bit more robust to a little bit of head motion, if it's critical. I've been monologuing for a while now, so any questions so far? Yes?
Why are certain parts of the brain more prone to drop out than others, and what causes it?
Okay, so I'll say to the mic, so people online can hear, why are some areas more prone to drop out than others? There are several reasons. One is pretty much boundaries between different types of tissues. Cause more distortions in the field, and that translates with the way we do fMRI imaging to often lower signals. So like the transition between your sinus in your nose or your ear canals and your brain are those areas that often have a lot of dropout. Also examples like if you put someone in the scanner who has, if you put someone with magnetic metal, you're in trouble. But if someone has like metal fillings that aren't magnetic, that's also that having that extra metal is going to distort the magnetic field and cause dropout near that area. Yes.
I have a question. How dependent are these factors that you listed here? Are they dependent on the scanner you use?
Yes and no. Actually, I'll just say yes. The biggest one is field strength. So field strength is gonna, ignoring everything else, field strength is gonna give you more signal to noise. You're gonna, more, just straight out more signal for everything else in the same. But these distortions and these different things that cause artifacts will sometimes be more. So if you do the exact same scanning parameters on one of our 7 Tesla scanners versus 3 Tesla scanners, you're gonna get higher SNR on, by the way, we can't actually do that because there's other hardware that's different too, but like if we could, you would get better SNR at the 7T and you would also get more distortion and more dropout at 7T.
How about like comparing 7TA and 7TV? Would you have to design your study specific to the scanner you choose?
You would not have to design it specific to the scanner, but there are variations. So every software change and hardware change is going to affect things. So there's been a few cases here that if someone wants to pick up, they could, but in the back of the room. But there's been a few cases here where there was a reconstruction variation in scanners, and when someone moved to another scanner, they were checking and their data quality shifted radically, and it took a while to realize what was happening. So things like this absolutely do happen, but it's not. And then just like, we've had 3 Tesla scanners for 20 years now, and 3 Tesla scanner that is built right now using cutting edge technology is going to be a lot better than a 3 Tesla scanner built 20 years ago, because there's just a lot of changes that have been made that make them better. So it's hardware is definitely more than just the field strength, but even with like the exact same model scanner and the exact same everything, there are some surprises, and even things like shimming and calibration varies across scanners. You do see differences.
Thanks.
Okay. I'm not gonna sort of go, like, I was kind of like listing off a lot of stuff. I'm not gonna go through all of them, but like, this is just one example that I think people talk about a lot, which is TR, which is our sampling rate, so the speed of scanning. So if you collect a volume of the brain every half second, 2 seconds, 7 seconds. If you collect a shorter TR, so get faster data, you get finer temporal resolution. So that seems like a great thing. Because we're measuring hemodynamic responses, which typically evolve over 5 to 10 seconds. Going super fast for most of our studies isn't gonna like give you a huge boost on those study designs. But more and more, we've seen studies that you actually can resolve really short things in hemodynamic, like, sub-second even in hemodynamics, if you design your study right. So if you're doing a study that you really want to resolve that really fast stuff, then you might want to push to shorter TRs. If that doesn't matter for your study design, it doesn't matter. The other thing with faster is like we know respiration and cardiac signals are huge artifact sources. So if you collect fast enough, you can actually, you have better chance at removing those noise sources. The trouble is your heart is beating, potentially faster than 1 beat a minute, 1 beat per second. So even if you're collecting a 700 millisecond TR, you're not necessarily gonna like be able to just filter out your heart rate. So it's not as clean, but it probably is better than trying to remove heart rate and respiration with a 3-second TR. But on the flip side is if you're going faster, it's harder to get, you get more volumes, you can average more also, so that's a signal improvement. But every volume is for various reasons, shorter TRs is gonna like make your data a little bit more noisy. Especially if you're adding, usually we get shorter TRs by using these things, different acceleration methods, which are sort of collecting a fraction of your full data set and putting it back and reconstructing with only parts of your data. And those are critical for these super fast TRs, but potentially add more artifacts and more noise. So it means you just have to sort of pay attention to your data and what the costs of these acceleration methods are for specific studies. And also there's possibly less brain coverage. So like if you really want a 700 millisecond TR, it's going to be a little bit trickier to get whole brain. So you have to decide again, like do you need, how important is your cerebellum to brain function? So if you decide cerebellums aren't that important, you can remove the cerebellum. But if you think the cerebellum is important, then pushing your TR super short might have issues. Any questions on that? And this is sort of just another example, like another parameter that a lot of people talk about is voxel size. And here it's, conceptually it's very, it's a little bit easier in that we're looking at the brain, everything is like on the microscopic level. So if we're collecting 3 millimeter voxels, 3 by 3 by 3 millimeter voxels, we're sampling, huge amount of neurons in every single voxel, and we're getting gray matter, we're getting white matter, we're getting CSF in pretty much every voxel. But if we go smaller, we can get, purely in gray matter and better resolution, and we can resolve differences in small brain regions better. Or we can even go down to like sub-millimeter and potentially get, cortical layered differentiating information. But we also get more noise. And the noise scales with the voxel size. So, 3 by 3 millimeter voxels is 27 cubic millimeters, and 1 millimeter voxels is 1 cubic millimeter. So that is, and your signal to noise scales roughly with that. So you're getting a nearly a 30-fold drop in signal to noise, with all other things being equal. But I guess in this data, it's not quite that big, but it does vary a little bit. So like in this picture, this left-hand side is 0.75 by 0.75 by 1 millimeter voxels. And you can see the temporal signal is not signal to noise, so it's a little bit more stable, which is why these are a little bit closer. But this ranges up to about 60 temporal signal to noise. You go to 1.5 millimeter cubic voxels, that's 70. The yellow here color is about 70. You go to 3 millimeter cubic, the temporal signal noise is 112. So you can see, and here sort of on this study, you can see as your voxels shrink, your temporal signal noise drops as well. So this is one of those things that you get noisier data, but more precision. The one other interesting thing on this noise versus precision thing is what's like a little bit hinted at earlier. If you have 3 millimeter voxels with better signal to noise, but they're sampling cortex that's doing 3 different things and some CSF, you might actually be getting better quality data with a voxel that is purely in gray matter, and more focal. So this is one of these things that I'll get to later in the piloting section, where understanding how the relationship between these two interact and really looking at this stuff in your study is critical. But again, the other thing with smaller voxel sizes is it's slower. It takes more time to acquire smaller voxels, so it's hard to get both small voxels and fast data. So so in a lot of studies, when you're designing the study, there's this conflict between how large a voxel do I need and how fast do I want to scan. And just to sort of list other things to think about, so I mentioned acceleration methods. I'm going to give a talk on multi-echo fMRI later on this summer, but it's another option choice. It's another choice to consider with different acquisitions. There's non-bold fMRI, non-bold contrasts, like VASO, which is often used for vapor, which are often used for these layer studies with really high resolution. There's this stuff called 2D versus 3D acquisition, which means, are we collecting sort of a slice of data or a few slices of data at a time, or are we collecting the whole 3D volume, in one excitation pulse at a time? And then there's even these parameters that people don't tend to think about, like flip angle, which is sort of how much do we how much do we inject signal in at the beginning with our excitation pulses that can matter to a study through various ways. So before I go into my next slide, any questions so far? Okay. Yeah.
And this is kind of building on Josh's question a second ago, but how much this is all, I can all picture this if you're doing a study on one scanner, one study team is doing a scanner, but do you have perspective on big studies that, maybe are lots of teams across the country doing it and in Connecto, ABCD, that kind of thing, how to think about these kind of decisions when you need to accommodate for lots of different setups and places in the world?
So there's a few different ways to do that. Probably the ABCD study is one example that did this, and there's another, ADNI is the Alzheimer's study, where they said, these are the goals of what we're collecting, and here are parameters, and they did a lot of piloting. And they actually said, for this brand scanner, here are the pulse sequences to use to get these parameters. For this brand scanner, these are the pulse sequences. And following on Josh's question, they're not the same. So I know ADNI, I don't think ABC did this, but ADNI actually created a phantom that you're supposed to use. So just sort of a specialized jar of oil with some other stuff that you're supposed to use at every single site to sort of collect consistent baseline data on how things vary across the sites. So it's hard, and it involves everything I'm saying here about running your own study on one site holds times 10. And speaking of the HPCP study, I will give a mildly provocative case study of this. So one thing I want to stress is when I talk about don't just grab other people's pulse sequences, there is no such thing as a gold standard data set. I've definitely heard people, talk. So the Human Connectome Project is a massive project where they collected, over 1,000 scans with, a bunch of stuff, and it's used in a lot of studies because it's widely available, it's easily accessible. And I've heard people call it a gold standard data set and say we downloaded it, we're fine, we can just use it. They've done everything right. So here are data sets from two different studies. The first one is Human Connectome Project. The second one is another really wide shared data set called ABIDE, which is an autism study. So these are the raw EPI images. You can look at the Connectome Project. I talked about distortion dropout. You are getting quite a bit of dropout here. You can also see in the ABIDE study, we're also getting dropout here. So this is temporal lobe and orbital frontal cortex. We're also getting it here, but you can also see things are a little bit more distorted here. This is kind of the brain doesn't have swirls like this. So the raw data is definitely more distorted. You can barely see, if you look at the ABIDE data, you can see sulci. You can barely see sulci in this raw image up here. So just looking at the raw data, there's a difference. I talked about temporal signal to noise. So this is just a single subject that I picked genuinely randomly from the HCP permits. data set. And the max temporal signal noise is around 70. And if you look at the center of the brain, the signal to noise is around 20. Or some areas just complete dropout in the center. You look at the ABIDE study, max signal to noise is 120, and pretty much most of the cortex, most of gray matter is well over 100. So the difference, the Connectum project really wanted to prioritize these short TRs and small voxels. So like I said, you have to make compromises sometimes. They wanted to get, part of the study's goal was to really push the limits of what acquisition could be. So they went fast, so 0.72 second sampling rate. They used a lot of acceleration, this thing called multi-slice acceleration with a factor of 8. So they're collecting 1/8 of the total data set they could have collected per volume. And they used 2 millimeter voxels. While ABIDE was using a 2.5 second TR, an in-slice acceleration of 3 and 3 millimeter voxels. So you can see that there's radically different results. Now, are these both fine depending on application? Yes, but there are some applications where this might really matter. So, for example, like we look at the Connectum project, there's been hundreds, if not thousands, of publications using these data. If you look at the ones that have, gotten headlines, gotten in prominent journals, what's common with them? They use regions of interest that average across multiple small voxels. They do correlation or task studies that summarize data across time. Or they average across a large population. So like they're making atlases of brain regions across the entire 1,000 people. So these are strong studies. The data set was acquired well, and these are good things that came from these data sets. There are people who've tried other things with the Connectum project data that haven't worked as well. So studies that try to fully take advantage of that, both the short TR and small voxel size without averaging over ROIs, there's very few that have gotten robust findings. And there was a big discussion recently in the field about these brain-wide association studies. So that's comparing, individuals' data based on behavioral phenotypes to different measures. And those individual data sets are really low temporal signal noise, and they're really noisy. And just looking at these raw data, I am not surprised that this HCB data was not good at finding results for brain-wide association studies. I will note that I'm making a broad and not completely fair generalization here. I'm just showing you a random sample from that data set. I think the reason I'm picked on this one is I can punch up. The Connectum project is one of the biggest studies out there, and they're doing just fine. I'm not gonna pick out some random lab with 5 people and tell you how horrible their data is. So it's much easier to punch up at this data set that everyone says is great than pick on someone small. But I think the main take-home message from this is you can have great data for one application, but it might not be great for all applications. And you really need to identify and review what quality metrics are relevant for your application. Any questions at this? I had time, so we'll see how I go. I only have 25 slides, because there are some great questions, but piloting. So that's the second phase. So what is piloting? Piloting is you're collecting a small data set before your real study. So what are the goals of piloting? You're going to compare options for potential study design. So do you get what you want with 2 millimeter voxels? Or do you really need to go down to 1.5? Or is it fine with 3? If you do different acceleration levels, does that matter for your data quality? So you're comparing. Then there's also just making sure design decisions work as expected. So you have a plan for a study, you know what you want, you know you're getting, and you try it and you say, did I actually get what I expected to get? This is also useful for power analyses. So like if you're not sure what an effect size is, and you do something, you say the area I'm interested in seems to have like a 2% signal change. That's going to affect your decision on sample size much more than if it's versus a 1% signal change. That's going to affect your decisions on how you design your study and sample size. The other important thing of piloting is making sure your acquisition workflow works with actual people. So unquestionably, every time you design a study, it's going to be different when you're having an actual volunteer come to the scanner and being asked to do something. So it's everything from your behavioral analyses, making sure that they're responding to the task and doing it correctly, to are they falling asleep in the scanner? Do you have a workflow to get them in and out in the right amount of time? Do you have your sequences set up in a way that you can actually run? The other thing that I feel is a little bit neglected is piloting is a great time to decide how to log key information and store and process your data. So it's your first run through your processing scripts, and also your first run through, okay, I want to make sure that my data in the end is not going to be an absolute mess. And it's also, and similarly, it's also time to start making that quality assurance workflow, because you're finding these metrics that matter. Like, if you're expecting a visual response, are you getting a visual response? If you're expecting a hippocampal response, are you seeing a response in the hippocampus? I think I had this message before. Don't use scanning parameters just because they work for someone else. I had it before because it's a really important message. Don't use scanning parameters just because they work for someone else. If you're not an expert in MRI physics, there are things that might affect data quality that you have not thought about. So just as one example, I was talking about acceleration earlier. So we can do acceleration because the head coils we put around people's heads have a bunch of little circles, each recording data independently, and we can use those. And because we're getting sort of, nine, in this case, there's 9 circles in these two little mock-ups. Because we're getting 9 independent recordings, we can sort of, and they're scattered across space, we can use that information to collect less data and reconstruct what we missed. But it matters how they are set up. So like, if you have a head coil that has 9 coils arrayed in 2 rows, you can accelerate in this direction up to, a factor of 4, and in this direction up to a factor of 2. While in this head coil, you can accelerate up to a factor of 3 in each direction. So if you are using the exact same scanner and the exact same pulse sequence, and someone swapped the head coil to another one that has a different configuration. I mean, this is an extreme example. Like, if you're swapped with a head coil with a different configuration, then a sequence that worked for one person is fundamentally not going to work for the other. We just had a consult. I guess a bit back at a consult with someone who was scanning at another facility where they had a head coil with, I think, 16 channels, and they got someone sequence that had a very high level of acceleration that just wasn't going to work. And they asked the right questions at the right time and said, okay, we can't do that. But that's not always what happens. And I'll also stress that, like, if you're not an expert in MRI physics, you might not be thinking of head coil spatial configurations. But if you are an expert in MRI physics, I don't have to tell you this, because everyone knows that there's stuff they don't know, and they know they have to pilot data to see how things work on their actual hardware. So I'm going to switch the next section on data collection protocols. Does anyone have any questions before I jump to that? So I think the protocol is really, in some ways, it's just a really practical part. It's the checklists and workflows, both for regulations and safety. So like any study with humans, you have to collect information and store it and organize it. We want to make sure that you're putting someone in the scanner, you're not going to accidentally get them, injured. And experimental needs. You really want to make a workflow as much as clear as possible, especially on these larger studies or multi-site studies, so that things are done consistently. Then also, this is a good time to start to think about what to say. Like, there's the MRI data, of course, but you're, like I said earlier, collecting peripheral data. Do you want to collect behavioral? Are you consistently recording like the qualitative stuff at a scan? Like the person said, after run 3, like, oh, they sounded like they fell asleep. Thinking about what you're saving and how you're saving it is critical. And organizing it. So the consistent structure across individuals, both for data and information explaining. And I think a lot of people talk about data sharing nowadays, but the most important person you share data with is your future self. Because you're going to collect data now and you're going to look at it a year from now, and you want to have organized things that your future self a year or 5 years from now knows what you actually did. So if you are organizing your data that your future self understands what you did, you can probably share it with someone else as well. And also in this protocol is again, quality assurance, like this is when you really sort of hammer down, like, what are you gonna run on every subject at every point? Now, this is, I do not expect people to see this text. What this is on these questions I've been talking about, on, you know, what to collect and what to organize. Just last year, I was, you know, I helped publish this paper on quality assurance. And there is in the appendix, there is this checklist of a lot of questions to ask and, you know, think about for each study. So I'm sharing it here. These slides are posted online. So you can go look up this paper in the appendix if this might be useful for you for designing a study. So data collection. Any questions before that? So number one, if you've really given thought to your study design, really done good piloting, really set up a good protocol, then data collection is following a script. Doesn't mean it's easy, it doesn't mean it's not tiring, but it's following a script if you've done everything right. But the important thing is you want to pay attention when things go off script. So sometimes, you know, it goes off script, you have to log it, like subject had to leave the scanner in the middle to use the bathroom, or subject fell asleep in the scan, or headphones didn't work. So you want to log the things that break the script, but you also want to sort of pay attention, like if the same thing happens over and over again, you know, before you collect your 300th subject, you need to change your script. And in parallel to that is again, this quality assessment, quality control. You really want to do some level of quality control, if not during data acquisition, immediately, as soon as possible after data acquisition, because if there are fixable problems, you want to correct them, identify them and correct them before you collect a lot more data. And the sooner you're more likely to look at, you know, identify little anomalies in data sets or things that skew results at the point of data collection than when you have like 30 data sets or 100 data sets in the future, and you're going to sit down and try and look through everything separately. So the sooner you sort of identify issues, the better you are. And this, I think anyone who's worked in MRI centers long enough can share horror stories. Some of which we can put on YouTube and some of which we probably shouldn't. But the number of times people have collected lots of data and realized after the fact the data wasn't what they needed because they hadn't bothered to like even open data sets for a long time. There are stories, I'll leave it at that. And I think again, like this is my point of quality control all through this. All data sets have problems. If you're not checking your data, what that means is you don't know what your problems are. If you do check the data, you're probably still missing problems, but you're going to be missing fewer of them. So as far as checking data afterwards, I want to sort of give a quick example of a lot of us here use a software package called AFNI. And when you run the AFNI pipeline, it gives you it automatically creates a quality control report and gives you a lot of images that people can look at. And this is just a hint of part of that report to give people a sense of what's there. So it outputs the raw EPI images like I showed for the Connectome project earlier. So this is a data set. You can see that there's, you know, some dropout in the temporal lobes and on orbital cortex. There's a bit of distortion here. The image is brighter on the side, which is not atypical, but you can start looking at it, seeing if things look expected. Again, like expected, you should already know what you're expecting at the piloting phase. The big thing when you're at this phase is, you design your study, you know what you should get. This is the phase you're looking at, did I actually get that? You can look at, this is an example of they have this thing where you can align your EPI image to the anatomical. So the red is the sulcal boundaries of the anatomy, and the background is the aligned EPI. So you can see that in this case, it might be small for some people, but they're lined up pretty well. You can put the fMRI data that had the voxels that had good data over the anatomical, and you can see what areas you missed. So in this case, I'm clearly losing a chunk of temporal lobe. I'm clearly using a bunch of this orbital frontal cortex. I've lost a bit of the cerebellum, and I've lost a chunk of brainstem. So for this study, that's not a huge deal, but for other studies that could be critical. You can get head motion traces. So this subject their head moved 0.25 millimeters across the whole scan. So that's very low. But you can see that there was a slow drift here. And, this was actually three different runs. You can see their head kind of jerked a bit between the runs. And this was a task fMRI study. And part of the quality control report outputs when task events happened in your model. And this can be quite useful because every so often you mess something up in your design and you look at it and in a second you're like, okay, that looks wrong. Like all your events happened in like one small section or something else is wrong. So this is a good thing to check on. This report also includes censored volumes that were removed for some reason. And sometimes you can see that the censored volumes, are always happening during the same tasks or not. So in this case, these light red areas, there's not much censoring, so it's not a big deal. And lastly, you can see your rough stat maps. This was a visual audio task, and this is sort of the overall contrast map. And you can see that I'm primarily getting visual and audio signal. And I'll say that you don't want to sort of, in quality control, say how good are the results I care about. So like, if your question is, if you're looking at something subtle, you don't want to say throw out data that's not good. But like, if I'm doing a visual audio task, looking at my map for just the overall visual audio response is a great measure of like, it looks like it's supposed to. Like there are some data sets where you might be getting signal in, ventricles or edge of brains or outside of brains, and that's the sign something is wrong. This one looks pretty reasonable. Another thing, especially for larger studies that I've started to do, is you can make, just like this map is how much of the brain was covered in a single subject, you can sort of make an overall map of coverage across the population. So what you can see is in this population, everyone's losing a bit of it. These are two different data sets. This one is losing a bit more of the temporal lobe than the other one, and the subjects with the voxels with data from all the subjects varies a bit. And this, I think, is particularly neglected. A lot of people do regions of interest studies of like take regions of interest across the whole brain. And if 5% of your population is missing part of a region of interest and you're not paying attention to that, then you're effectively comparing different brain regions between different people. Any questions so far? Okay, so analysis interpretation, my other general method is I can't cover it all. Like there is so many different ways to analyze data and so many ways to interpret it. I'm barely gonna try, but I'm gonna give 3 messages that I think are true for pretty much any fMRI study, which is everything we're doing programming in scripts. Whatever you do, make sure the scripts fail in clear ways. So if there's a missing data set or there's some issue, it should tell you or it should crash. And it shouldn't be sort of hidden beneath sort of different layers that you kind of lose it along the way. Save intermediate processing data, because if you do see issues, that's the stuff that's gonna help you figure out what happened. The one that I wish I didn't have to say, but it is shockingly not always done, is look at your data. You wanna look at your EPI data, you wanna look at your maps, you wanna look at your time series, because that's where, if there are issues that those problems there can drive mistakes and errors in much more upstream analyses methods if you don't look for it. And lastly, track provenance, which is, know how data were processed and created. So communication was the final phase. So I think one message I want to pull out there is show as much of your data as possible. This could be sharing data, but it also matters in images. So this image was based on a study that had a large number of groups, I think 70 groups, I'm showing 25 here, all process the exact same data set with the exact same goals and create activation maps. And what you could see is across these 25 studies, the exact same data, people are getting a fairly large variety in the areas that are active or not. So sometimes we're getting activation here, sometimes we're not, sometimes, a bunch of these have, big negative activity here in the contrast, some not at all. And this made a lot of news because people are like, fMRI is unreliable. We don't, every we go to analyze data, we get totally different results. So Paul Taylor, who's here and runs the AFNI group, said that a lot of this issue is coming down to how you set that precise threshold. So if instead of instead of visualizing just by a binary visualization of your threshold, you can have that threshold, but add this translucency layer for the stuff below threshold. And what you see here is across these images, there's a lot of similarity. So the variation between these results isn't that they're not getting different findings. It's that that threshold it's very sensitive to that threshold, and slight shifts of thresholds are essentially giving you different results, giving you different binary maps for what's essentially very similar results. So this is, I wanted to bring this up because this is sort of a newer discussion on using these translucency maps to sort of both clearly communicate what's statistically significant, but also show a little bit of what's below, so you can get a better sense of the whole data set. And I highly recommend taking a look at this paper as well. Just finally with communication, it's a lot easier to share coding data if it's set up with sharing in mind. I repeat what I said earlier, that you're sharing with your future self. And if you do everything with the plan to share with yourself in the future, you're gonna be in a good place. The one that not many people do, but I think is gonna become more and more important is if you're sharing data, share acute quality assessment measures. Especially with these big data sets, I've been hearing more and more stories of like, hey, we downloaded this big data set and we run QA and we found these 10 subjects with a problem, or we ran QA and we found these other subjects with a problem. So the more people start sharing this information with their data, the more we're gonna be benefiting the field, making our data more useful and saving people a lot of time. And finally, my main take-home message is make time to think about 3 choices at every step of the study. If I haven't said enough, quality assessment really is a critical part of every study. And I've gone through a lot of content here, and I've waved my hands over details more than I focused on things. But I think a real key thing to keep in mind is no one is an expert in every step of every neuroimaging study. In behavioral psychology, cognitive science, clinical medicine, neuroanatomy, physics, stats, software development, communication, the number of people who are true experts in all these areas are extremely few. So there's going to be some aspect of a study which you don't know and you're not capable of knowing in the amount of time it takes to actually design your study. So learning what you don't know and where you need help is almost as important as what you know. So hopefully through this talk, I've gone through lists of stuff that might give you a sense of where you have strengths and where you don't know, and gives you a sense of like, if you're designing your own study or helping someone with a study, thinking about where you actually should seek out help as you go. That's it. A few minutes over, but I'm absolutely happy to answer the questions as long as people have questions and they don't kick us out. Okay. Any questions online? Okay.